Yes.
Okay. You have a resource, okay? It may be anything. It may be a lecture room. A supercomputer. Or an electron microscope, okay? Or in the computer, for example, it might be CPU, memory, any kind of resource that needs to be shared among multiple people, okay? And many people request to use the resource for periods of time. Okay, for example, it might be multiple processes that want to use the CPU or memory, and each one wants to use it for a certain period of time. Or it may be seminars that need to use, or classes that need to use a specific lecture room for a certain period of time. So there are requests. A request takes the following form. Can I reserve the resource starting at time S until time F, F for finishing, okay? It's like exams or lectures. Can I use it between 10 and 12, etc.? Okay, that's a request. We assume that and that's a pretty realistic assumption that the resource can be used by at most one person at a time. At a time, okay? So a scheduler wants to accept a subset of these requests. Rejecting all others. So that the accepted requests so that the accepted requests do not overlap in time. Because if they overlapped, excuse me. Okay. If they overlapped, then we wouldn't adhere to the requirement that it can be used by at most one person at a time. Okay, so they cannot overlap. So, of course, some of them, for example, I want to have a lecture between 10 and 12, and somebody wants to have a lecture between 11 and 13, for example, 11 and 1. So, of course, you can pick only one of them because otherwise they would have to overlap. Okay, you have to reject one of them. The question is which one? And there are all these different types of requests with different availability times. we have n requests labeled 1 to n, with each request I specifying a start time.
Hocam ekranda şu an Teams gözüküyor. Bende mi öyle bilmiyorum ama.
Öyle mi? Hayır. Şeyi açtım. OneNote'u açtım.
Bende öyle o zaman.
Başka OneNote ekranı göremeyen var mı?
Ben görebiliyorum hocam.
Tamamdır. With each request I specifying a start time SI. SI and a finish time FI. Okay. Each interval I now also has a value. Has a value or weight VI. Okay. So some requests are more important than others, let's say. So two intervals are compatible. Two intervals are compatible if they do not overlap. That's something we already said. The goal is to select a subset of these requests. I think the internet is slow. That's acceptable. 3 people are using it at the same time. The goal is to select a subset of these requests, a subset as of mutually compatible intervals. So as to maximize the sum of the values of the selected intervals. So it's like I want to maximize my profits, kind of, okay? I in S, VI, okay? I want to maximize my profit. I want to select intervals so that they do not overlap in time, and the total value of the intervals that I selected is maximized among all possible selections, okay? Suppose that the requests are sorted in order of non-decreasing finish time. Okay, let's say F1, F2, etc. Okay, Fn. We say that a request I comes before a request J if I is less than j. Okay, that's what we say. We order the requests according to their finishing time. We say that one comes before that if its finish time is less than the other's finishing time. Okay, and PJ. Now I will describe a dynamic programming algorithm that solves this problem exactly, finds the optimum solution always. Okay, let me define some other term. PJ is the largest index J the largest index I that is less than J for an interval J. Such that intervals I and J are disjoint. Okay, so it's like for an interval J, for example, there are other intervals too. Some of them intersect with this request. Okay, it could be something like that. Okay, the largest index, such that the largest index, yani, I mean, if with the finishing time, because they say that we say that it comes before that, if its finish time is less than this one. For example, here, the largest one, the one with the latest finishing time, that also coming before it. Okay. It doesn't have to be the one that overlaps, because that it might be the case that J is something like this. Sorry, not this one. Sorry. There might be other ones, okay? But you have to select the ones such that I and J are disjoint. So I cannot select this one or that one here. I have to select this one. This is the answer. And here, I cannot select this interval. I cannot select this interval because it's not disjoint with J. But I can select these two, but I select the one that has the largest index, so that has the closest finishing time according to the finishing time of J. So it has to be this one. Okay, so this is PJ. And here this is PJ. Is this clear? The leftmost interval before I begins. Okay, let me define it this way. Is this clear, everybody? I will give another example. Here, these examples I just made up, but I have other examples from my notes. Let's say indexes 1, 2, 3, 4, 5, and 6. Okay, so this is V1, is 2. This is V2, it's 4. V3 is 4. Let's say V4 is 7. V5 is 2, and V6 1. Okay. For example, let's write the p-values. So these are the intervals. Okay. let's write the p-values for these intervals. P1. There is no other interval that comes before this one, okay, be it disjoint or not disjoint, because it's the one with the earliest finishing time. So it's 0, okay? There is no interval. With P2, there is an interval with finishing time less than that, and that is 1, interval 1, but it's not disjoint. So there is no disjoint interval. So P2 is also 0. With P3, I don't know if it's evident here, but maybe I should have drawn it better. P3 and P1 are disjoint, okay? Because P3 and P1 are disjoint, only interval 1 comes before it, so P3 is 1, okay? So P4 is, it intersects with all others, okay? That comes before it, so for P4 it's 0, okay? With P5, the options are 1, 2, and 3 because it intersects with 4. Because the options are 1, 2, and 3, among these 3 options, the one with the closest finishing time is 3. So P5 is 3, okay? P6 is something else. Excuse me, I need to, I'll be back in a minute. Okay, I'm back. Can you still see my screen? Yes?
Yes, we can.
Okay. So P5 is 3, and let's talk about P6. With P6 intersects with interval 4 and interval 5, so we can't have them. And again, among intervals 1, 2, and 3, the ones with the closest finishing time to it is 3. P6 is 3, okay? So is this clear what the definition of PJ is? Because we will describe our dynamic programming algorithm according to this definition, okay? We will talk about an optimum solution, etc. Again, as the previous problems, I'm thinking from the end to the front, okay? I'm thinking backwards direction. So consider an optimal solution. And think about in an optimum solution, order them according to their order, their finishing times. Order the intervals in an optimum solution. I'm not looking at all the possible cases. I'm thinking about. I'm talking about a solution. Okay. Either let's say that I have intervals from 1 in that from 1 to n ordered, like just like in this figure. Think about the last interval in this ordering according to finishing times, okay? Think about this one. So this can be in the optimum solution. Maybe it is in the optimum solution or it is not in the optimum solution. There are 2 cases, right? And I have to have one of these 2 possibilities in the solution or the last one. So if it is in the solution, then no interval with strictly between Pn. Pn is, remember, disjoint with that, okay, the largest index, and n can belong to the optimum solution by the definition of Pn, because all the intervals like that are not disjoint with n. Okay. For example, let me write it and then I will explain it in this figure also again. Either interval n belongs to O star or it does not. Okay. If it is in the optimum solution, then no interval indexed strictly between Pn and n can belong to O star. By definition of Pn. No interval indexed strictly between that. Why? For example, if this interval 6 is in the solution, then P6 is 3, right? So it's this one. That's P6. The ones between 3 and 6, actually, which are 4 and 5, by definition of Pn, they have to intersect with 6, okay? And they do here, 4 and 5, right? Because otherwise, we would have included them as Pn if they didn't overlap with interval 6, okay? So if I have 6, interval 6 in my solution, then I cannot have 4 and 5 in my solution. That's for sure, right? So when I want to solve the remaining, then I have to solve the same problem optimally with intervals only from 1 to 3, okay? And then I add this interval 6 to my solution, and then I will get the optimum solution in case that interval 6 is in the solution, okay? Then I would have to select it. No interval indexed strictly between Pn and n can belong to O star by definition of Pn. Also in this case, then O star must include an optimal solution to the problem consisting of requests 1 to Pn, okay? I have to solve it then, because otherwise we could replace the optimum solutions choice of requests from here with a better one with no danger of overlapping request n. Okay, with no danger of overlapping request n. If it's not in the optimum solution, then it's even easier. Then I just solve the same problem for requests 1, 2, and -1. Okay. If n is not in the optimum solution, then is simply equal to the optimal solution requests 1, 2, and -1. Okay. So I can, my dynamic programming algorithm operates with between these two cases. Select the one that has the highest value, with including n or not. Okay. Let O star j denote the optimal solution to the problem consisting of requests 1 to j. Okay. Let opt j be the value of this solution. Define opt 0 equal to 0. Okay. We are selecting O star, the actual optimum, as opt n. Okay. Now we are ready to write the dynamic programming recursion. Opt j is the optimum solution for requests indexed from 1 to j. Okay. It's the maximum of these two cases, which are, if I have Vj in my solution, in that case, I have the value of j contributes to my solution, plus opt pj. Pj is as we defined, okay? The pj is the index of the request that has the closest finishing time among the requests that come before j and do not overlap with j, okay? Vj plus opt pj. And the other case is when I don't include j in my solution, it's opt j minus 1, okay? Okay. So now request j belongs to an optimal solution if and only if Vj plus opt Pj is greater than or equal to opt J minus 1. Okay? So this way, I can write the pseudocode for my algorithm as follows. Compute opt J is if J equals 0, then return 0. Else, return maximum of Vj plus compute opt J, compute opt Pj, sorry, and compute opt J minus 1. And okay, are there any questions about this the dynamic programming algorithm for the weighted interval scheduling problem? Okay, if not, then I will start with our last chapter called greedy algorithms. So this is all for dynamic programming. If you have questions about dynamic programming, please ask them. Okay, this is your last chance to ask questions during the lecture about dynamic programming. So I will give a little bit of the characteristics of greedy algorithms, what we mean by greedy algorithms, and then I will remind you the minimum spanning tree problem, Prim's algorithm and Kruskal's algorithm. You already know them, but they are very good examples of greedy algorithms. Then we will solve this interval scheduling problem, the same problem that we solved with dynamic programming, now with greedy algorithms. Okay. So the formal definition is more or less like this. It's called greedy if it builds up a solution in small steps, choosing a decision at each step myopically to optimize some underlying criterion. When I say myopically, I mean that I look at only its short-term consequences, not in the long term. Okay? It's like it makes sense now to make this step, etc. Actually, first of all, greedy algorithm, the greedy design technique is simply an algorithm design technique, just like the others. Okay? It's an algorithm design technique, just like the previous ones. It does not guarantee us an optimal solution in every problem, okay? Or even for the same problem, you may come up with a greedy algorithm, one, let's say, that gives you an optimal solution, but some other greedy algorithm, some different greedy algorithm that somebody else came up with, or you came up with also, may not give you, guarantee you an optimal solution. Okay, it's just some tool you have. You, for certain problems, maybe it's impossible to come up with any exact algorithm or any greedy algorithm to solve it, but sometimes yes, sometimes no. Okay, so it's just a tool to attack the algorithm design technique, first of all. Secondly, it's actually very natural. If somebody asks you about a problem and you need to solve it, I mean, usually, and you have no idea how to solve it, usually the first one that comes to your mind is a greedy one, okay? And it's actually similar to many decisions that we make in life, okay? Sometimes you have to make a decision and you, according to your experience or anything, or logic, I mean, assuming that it's a rational decision, it's not an emotional decision, okay? It's a, you take the step that seems to be more rational at that time, okay? Because you may not be able to foresee what you will see in the future, okay? So greedy algorithms are very natural in that sense. So I will talk about the minimum spanning tree and Kruskal's and Prim's algorithms, which are very typical examples for greedy algorithms. Okay, you already know from your data structures course, MST. Okay, Prim's algorithm. Just remember it. What does it do? It starts with a root node. Start with a root node. And greedily grow a tree outward, okay? So you start with a root node, some node, you pick the edge among all the other edges, you pick the one that has least cost, okay? Because it makes sense. You came here, then among this, in this vertex, you add one other one, again, with the other possibilities, you pick one edge, etc. Okay, so you grow this tree outwards in the Prim's algorithm. Just remember, okay? That's why it's greedy, because first of all, it builds up a solution in small steps. You pick one edge at a time, always, and you choose a decision at each step myopically. I mean, I say myopically here. For example, I pick the edge that has the minimum cost here, but I don't know, maybe in the future, it will lead me up to edges with very high cost, right? I mean, for this particular problem, this algorithm gives the optimal solution, but in general, I didn't take into account what might happen in the future. I just looked into this neighborhood and made a rational decision for that one, okay? So I picked this one to optimize some underlying criterion. So of course, the decision I make should be compliant with my criterion. My criterion in minimum spanning tree was to minimize the total cost of the edges, okay? That's why I picked the edge with the minimum cost in that neighborhood. So with Kruskal's algorithm also, the logic, although the operating principles are a little bit different, again, the logic is the same. It's again greedy, okay? Successively insert edges in order of increasing cost. Okay, in Prim's algorithm also I pick the edges such that the edge I pick does not create a cycle. So I maintained the property of it being a tree and I grow that tree outwards, okay? And in here, do not insert an edge again if it introduces a cycle. This time I don't grow it from outwards. But let's say I have the graph somewhere here, I pick the minimum cost edge. And another, the edge with the second minimum cost maybe is somewhere here. A third one, maybe here. A fourth one, if it's here, now because it would introduce a cycle, I don't include it in my solution. I pick the next one, which is here. Okay, so eventually they form a tree. Okay, that's what Kruskal's algorithm is, and it's also greedy. Okay, some other algorithm I will just describe, another greedy algorithm. I will write it down and then we will take a break. Another greedy algorithm. Remove edges starting from the highest cost. So it's like the reverse of Prim's algorithm. Highest cost. Remove the edge if it causes disconnectivity. Okay, the edges that I remain with are sorry, not remove. Don't remove the edge if it causes disconnectivity, because if it causes disconnectivity at that time, then it's a cut edge, like it's we have and we want a tree in the end. So this is like the reverse of Prim's algorithm, and the ones that the edges that you end up with that you cannot remove anymore in the remaining ones are the ones that are in your minimum spanning tree. Okay. These are three very simple examples and for greedy algorithms, but very nice examples for you to be able to grasp the nature of greedy algorithms. So we will take a 10 minutes break now, maybe 13 minutes, 2:35. We will meet and we will continue with greedy algorithms, this time a little bit for the same problem, the interval scheduling problem that we saw the dynamic programming algorithm for. Now, for the same problem, we will approach it from the greedy perspective. Okay. Take a break. I'm not. Okay, let me close it, or okay, let's not close it because it's already recording, and we will have a break now. Okay. See you in 10 minutes. Hi guys. Now I will talk about, by the way, can you hear me?
Yes.
Duyabiliyoruz hocam.
Okay, thanks. Now I will talk about the interval scheduling problem. The greedy algorithm stays ahead. Stays ahead, okay? So let's Si be the starting time of request I. And Fi be the finish time of request I, okay? We say that sorry, I'm waiting for this. It's a little bit slow, so. We say that a subset of the requests is compatible if no two of them overlap in time and our goal is to accept as large a compatible subset as possible. Okay, so it's the maximum size. So the basic idea is the following. Use a simple rule to select the first one. The first request I1. Reject all requests that are incompatible with I1. Then select the next request I2. And again, reject the ones incompatible with I2, etc. Continue until we run out of requests. Okay. So I hope you got the basic idea. So the question here is, which simple rule should we use? So I have a set of requests. Okay, maybe these ones, could be others, I don't know, like this. It might be anything, okay? And here, the requests all have value 1. Okay, so it's a little bit different from the first one. Actually, it's the same problem. It's a special case of this first problem that we saw in the dynamic programming section, where all the weights, all the values of the requests are equal to each other. Okay, so we want to have maximum number of requests is the same as maximizing the total value in this case. So a simple rule to select it, that's the rule. For example, I have a rule. I don't know which one, but I have a rule. Let's say I select this one. I don't know. Then I select it. I remove the ones that overlap with it. Then I'm left with the remaining. So with the remaining, for example, I select this one. And then I reject the ones. I reject this one because it overlaps. And in the remaining, I have 2 other requests, and I select the same one of them according to the same simple rule, whatever that rule is. And I select, let's say, one of them, and now I am left with no other requests, and my algorithm ends. Okay. So which simple rule should we use? Any ideas? What would you do? You are given some intervals with certain start and finishing times, and you want to maximize, you want to accept as many requests as possible. What would you do? Any guesses?
Türkçe söyleyebiliyor muyuz hocam?
No, you can't. It shouldn't be a very complicated English sentence. So please say it in English, your idea.
First, I choose the first one.
First, according to what? With
We try to find a rule, right? We don't try
Yes.
to find the
yes. When
find
you
the
say
answer.
first, for example, in here's, which one is the first? Like 1, 2,
Top
3.
top of the one.
Top, but why? I mean, I just drew it in the top. I could have drawn the same thing with the same intervals here. This is just the time. Okay.
Yes.
I mean, the top you said, but top and bottom are not important. It's just my way of drawing. It's the start and finishing times that are important.
Then I choose the longest one.
Okay, that's one option. Choose the longest one. But when you choose the longest one, why did you choose the longest one?
I don't know.
I mean, if it's longest, then it has a higher chance of overlapping with the others. Maybe you selected a very long one, but many other small requests overlapped with it. And let's say you had one request that is very long and many other small requests that didn't overlap with each other. You chose this one, but if you didn't choose this one, you would be able to choose the remaining, I don't know, 5, 6 of them. But you chose this one, and it's only one. You were able to choose one request.
Yes, it's bad idea.
Okay, maybe if you choose the smallest one, then would it make more sense? Because it has less chance of, I mean, it just intuitively, it has less chance of overlapping with other requests, maybe. If we do the reverse of what you says, the smallest ones, maybe. Another ideas, but still it's an idea. So another idea. Other ideas from the class? Okay, just one idea. I'm expecting another second idea. Once the second idea is available from another student, then I will continue the class. Okay. We selected the shortest one. No other ideas? You run out of ideas? Your friend's idea was good. Maybe is an idea that is, I mean, not very complicated. If you were a teaching assistant to allocate rooms for your final exams, what would you do? Which class would you schedule first?
Maybe we can choose the earliest one, 2, and then continue with.
Yes, that's
Others.
another option. Yes. Thank you for the second idea, but the same student. Okay. But I count it as 2 ideas. Okay, so let me continue then. Option 1 is just what your friend said. Select the available request that starts earliest. Okay. The one with minimum start time. I'll be back in 1 minute. Sorry for interrupting. My son's school is closed for 1 week due to COVID, so they have online education too. Select the available request that starts earliest, the one with minimum start time, SI, okay? It's like scheduling the exams that are at 9 a.m. at first, something like that, okay? So it is a greedy algorithm for sure, but does not yield an optimum solution always. Sometimes it can for some instances, but in order for us to be able to say that it's an optimal algorithm, then it has to give you the optimum solution on all possible instances, okay? The one with, so does not yield an optimum solution. So to prove that it does not yield an optimum solution, one counterexample is sufficient, okay? And it's something like this. Let's say you have a class that you have an exam that starts earliest, but it lasts for a very long time. All the remaining are later maybe, but they all overlap with this one. So if you schedule this one, then you have to reject all the remaining. But instead, if you rejected this one, then you would be able to choose like at least like 4 of them, okay? So if the earliest request is for a very long interval, then the algorithm fails. Okay, So we iterate in real life also. When you have a certain problem, you think of something that comes to your mind, find a counterexample, then okay, what is the weakness here then? Why doesn't it work on this counterexample? So maybe I can adapt my algorithm accordingly. Here, the weakness is that the first one lasted a very long time. So the fact that it's a very long request is a disadvantage of that request, okay? So then an idea might be to pick the short ones, because the short ones has lower chance of overlapping with the others, right? As we talked also before. So for instance, in this example, if I chose the short one first, then I would probably, I mean, maybe not on here, but on this example, for example. If I just selected the shortest one, that if that were my algorithm, then it would give me an optimum solution, okay? So the option 2 is select the request that requires the smallest interval of time. Okay, in other words, with minimum fi minus si. But I have another counterexample here. Because it's a short request, we intuitively think that it has less chance of overlapping with the other requests because it's short. So it makes sense. It doesn't, the thing is that it doesn't have to. For example, if my instance is like this, I have a small request and two very long requests, and these very long requests do not overlap with each other, but it overlaps with the small request, then my algorithm would give me this. But the optimum solution would be this one, okay? Even with option 2. Option 2 makes more sense than option 1, but still we are able to find a counterexample, an example where it doesn't give us the optimum solution, right? So let's continue thinking then. Okay, it didn't work here. So what else can we do to improve it? We need to adapt our algorithm. Here, the thing that matters is that the number of requests that request overlaps with, right? So the length of the request, we saw that it may not be a very good indicator of this number of overlaps. So let's change my criterion to the number of overlaps. For example, pick the request that has the least number of overlaps with the other requests first, right? So because if I select that request, then I will have to remove less number of requests from the solution, right? For example, on this example, it would work because the small one on the bottom intervals overlaps with 2 intervals, whereas the other ones, it's only 1, okay? So I would select one of the top, the top 2. Option 3. For each request, count the number of other requests. That are not compatible and accept the request with fewest number of conflicts. Okay. So I have a counterexample for this one too, but this time it's not very easy to find a counterexample. It's a little bit more complicated counterexample. Although it makes sense, it makes much more sense than the previous two solutions, still. So here, the counterexample is this. I have this, 2, 3, 4, and these ones, okay. 3, with the same start and finishing times here. Okay, so if I select the number of requests that are have the fewest number of conflicts, for instance, this one has 1, 2, 3 conflicts, right? This one, 3 conflicts. This one has 1, 2, 3, 4, 5, 6 conflicts. This one also has 6 conflicts. This one has 3 conflicts. This one has 4 conflicts. 1, 2, 3, 4. Yes, 4 conflicts. Sorry, forget about these. We don't have these requests. Okay, sorry. So this is not 6. This is 1, 2, 3, 4 again. This is 4 again. This is 3. Okay. So this is 1, 2, 3, 4 conflicts. This also has 4 conflicts. This also has 4 conflicts. This one has 2 conflicts. This one has 4 and 4 conflicts. Okay. So now what does my algorithm do? My algorithm selects the one that has the least number of conflicts. So this one. Okay. So it eliminates this one, eliminates this one. Because this is eliminated, now this is updated as 3, 3, and 3. And because this is eliminated, this is updated as 3, 3, and 3. So now I could have selected any one of these 3, but let's say I select them randomly, it might give me, so I select this one. Once I select this one, I don't have this, and I don't have the others. Okay. And here, let's say that I select this one in my algorithm. So I don't have this, this, or that. So my algorithm gives me 3. Okay. It gives me 3 requests. But if I had selected these 4, it would give me 4 requests here, right? So one more. So we can see in this example that option 3 also does not give us always an optimum, does not always give us an optimum solution. Okay? Is this clear? So we tried and tried and tried and we couldn't find. This is very little. In real life, you try sometimes for months, and it's not as simple as this. Sorry?
It's clear, but I don't understand why we use this algorithm, because we can't find the optimal solution. So why do we use?
First of all, to show you that we may have many greedy algorithms for the same problem. And now I will talk about another greedy algorithm that does give you an optimum solution. Okay. So the fact that it's greedy doesn't ensure you that it's an optimum solution, first of all. And secondly, to give you an idea of the process of designing a greedy algorithm, how you try other things, you see its weakness and you try to improve it, etc. And thirdly, for some problems, finding the optimum solution may not be possible anyway. So whichever algorithm you come up with has to be heuristic algorithm. Okay? Heuristic algorithms are algorithms that don't always give you an optimum solution. They are usually used for very hard, computationally hard problems for which an optimum solution is almost impossible. And you usually show numerically, like by simulations, running it on many examples, etc. And you show that, okay, it doesn't always give me an optimum solution, but the solution that it gives is very good, okay? It's acceptable quality, and it gives me a solution fastly in a reasonable amount of time, okay? So in practice, you may use these heuristic algorithms, especially for hard problems and important problems, the ones that are difficult to find an optimum solution and to an optimum polynomial time solution to. You come up with fast heuristic algorithms, maybe not an optimum, but still acceptable quality. For applications, this may be good enough, okay? I hope it's clear. Is it clear?
Yes, thank you.
Okay. So let's talk about an optimum option then. Sorry, I have to take this. Okay, from where we left off. Optimum option is accept the request that finishes first, not starts first, but finishes first. With minimum fi. It seems strange at first why it gives an optimum solution, but it does. Let's, in such cases, okay, in the previous ones, because they didn't give an optimum solution, it was sufficient to give a counterexample. But here, it's an optimum solution. It's good, but we have to prove that it works for all possible instances. So we have to give a formal proof, not a counterexample, okay? So the starting point. Is a lemma, okay? I won't give a proof of the lemma, it's obvious, but we need to say it. So that's why we say it. The algorithm alg returns a compatible set of requests A. So actually a feasible solution, okay? Proof trivially obvious. Actually, for all of these algorithms, because we reject the ones that are incompatible in every step, then this automatically gives us a compatible set of requests finally, right? So the lemma is now that it gives an optimum solution. Obviously, it gives a feasible solution. So alg returns an optimal solution. So let O be an optimal set of intervals. We will show that the cardinality of A is equal to the cardinality of O. Okay, let's think of an optimal solution. I don't know what the solution exactly is, but I'm just saying that its cardinality, the number of requests in that optimal solution, if it's the same as the number of requests that in the solution that my algorithm returns, then my algorithm also gives an optimum solution, right? And that's we will prove. We will show that stays ahead of the solution O. It means it in every step it performs as good as how the optimum performs. Okay, so let's give some other notations. Let I1 IK the set of requests in the order that they were added by the algorithm. Okay, note that in here A is K, meaning what the algorithm returns. Okay, and similarly let J1, J2, Jm be the set of requests in O, the set of requests in the optimum solution, again in the order that they were added to the optimum solution. Okay, our goal is to prove that K is equal to M. Okay, so it means that in the order that they were added, our algorithm gives the same number of requests as any other optimum solution, meaning that our algorithm is also optimum. Okay, so observation. Simply an observation. Our greater rule guarantees that Fi1 is less than or equal to Fj1. Why? So remember our greater rule. Our greater rule is to accept the request that finishes first. So if my algorithm selected I1 first, then it means that its finishing time is less than or equal to the finishing time of all the other requests. That's why my algorithm selected it, okay? That's why fi1 is less than or equal to all the remaining requests, including fj1, okay? So fi1 is less than or equal to fj1. I hope this is clear. Is this clear? Any questions about this? Yes, no? So my lemma is that that's what I will prove. For all indices r less than or equal to k, we have FIR is less than or equal to FJR. Okay, that's my rule. Actually, we have 5 minutes, and this proof is a little complicated. Okay, I can finish it in 10 minutes because we started 5 minutes late, right? Okay, I will finish this one, and then we will continue tomorrow. So, for all indices are less than or equal to k, that's what we want to prove. We prove by induction. First rule of the induction, basis case. For r is equal to 1, it's already true. We said it here. We said it here. Okay, it's already true. Now, let r greater than 1. Assume that the statement is true for r minus 1. Okay, assume that it's true for r minus 1. That's my induction hypothesis. So it means that my induction hypothesis is f I r minus 1 is less than or equal to f j r minus 1. Okay, that comes from the induction hypothesis. Okay. Now I want to prove that if IR is less than or equal to FJR, I know that this is true. How do I prove the previous one? Okay. So to prove the previous one, to prove this, assume the reverse of this and obtain a contradiction. Okay. This is true. The reverse of this is true. And I will obtain a contribution. It will mean that the star here, this is true. Okay. So to obtain a contradiction, now assume that if IR is greater than FJR. Okay. Assume the contrapositive. But this cannot happen. Why? How does my algorithm behave? My algorithm always chooses the one with smaller finishing time, right? But my algorithm, when my algorithm selected IR, JR was available. But my algorithm selected IR. It always chooses the smaller finishing time. So this cannot happen. Because AUG always chooses the one with smaller FI. More precisely, since optimum solution O consists of compatible intervals fjr minus 1 is less than or equal to sjr, right? Because it's compatible. The starting time of JR is always after the finishing time of the previous one. Otherwise, they would be overlapping, and the optimum solution or any feasible solution would not select this. The interval JR is in the set R of available intervals at the time when ALK selects IR. Okay. This is since f IR minus 1 is less than or equal to f JR minus 1 due to induction hypothesis. We have f IR minus 1 is less than or equal to S JR. Okay. So it's like f IR minus 1 is less than or equal to f JR minus 1, and f JR minus 1 is less than or equal to SJR. So it was available, but it didn't select it. So that constitutes a contradiction. ALK selects the available interval with the smallest finishing time. Since JR. Okay, so this is the lemma. Now the theorem. Theorem is ALK returns an optimal set A. Okay, and the proof we will continue tomorrow. Before ending the lesson, I want to ask you, is everything clear with the proof of the previous lemma that for all indices R less than or equal to K, we have FIR is less than or equal to FJR? Is this proof clear? If not, then I can go over it. Okay. If it's clear, then tomorrow we will continue with the proof of this theorem. And then I will give you another example, scheduling to minimize lateness and exchange argument. If time permits, we will finish that. And it seems that we will be able to finish it in 1 hour or maybe a little bit more than that. For tomorrow's lesson, we had the lecture at usually at 10:30 regularly. I may be updating the time. Okay. I will announce it on Teams if I do so. If not, then the default time for the lecture is 10:30. Okay. Bye.
Bay bay hocam.
Bye bye.